Right, so PD interactions. Okay, so that stands for permanent dipole Okay, so what I mean is when we answer a question on this, it's such a mouthful, but it's the easiest way to describe what it is. Okay, it's a permanent dipole interaction, PD. Okay, and then if you answer a question, if you do that, put it in brackets, then therefore refer to it as PD. Okay. Now, permanent means that the dipole is not changing. It is what it is. Okay, and the reason it gets called permanent dipole is really in respect to London dispersion forces, which are induced dipole. So these ones are permanent, but the London dispersion ones are not permanent, they are induced. Okay? So it's mentioned as that in respect to that. Okay? Right. It occurs when there is a difference in electronegativity. Okay. Now, often there's a difference in electronegativity, but it's not a polar bond. Okay. So when I mean a difference in electronegativity between, let's say, atom A and atom B, a difference in electronegativity would leave one delta negative and one delta positive, and the reason for that is that B has a higher electronegativity and is pulling the electrons towards it. So the electrons between the bond would not be shared equal in an equal distance between the nuclei, but actually closer to one atom than the other. So in this case, the electrons that are being shared may be closer to B, which means if you were to look at B, there would be a greater net charge of the electrons, leaving this one slightly deficient of electrons. Okay. Now, a difference, we use this as a benchmark. Alright, so I think something like, is it 2.5 and maybe 2.1 or thereabouts. Use a carbon to hydrogen bond as a benchmark because it is not considered a big enough difference to be a polar bond. Okay, so this is not a polar bond. Okay, the difference is just not great enough, which means all alkanes, alkenes, cycloalkanes are non-polar molecules, and the only forces between the molecules are London dispersion forces, which we're going to read on. Okay? So it has to be a difference in electronegativity that's greater than that. Use that as a benchmark. Okay? Right, so one of the most important things that must be mentioned here is the spatial arrangement of the bonds lead to a molecule becoming polar or non-polar. Okay, so what that means is if two atoms within a bond, let's say A and B like before, have a difference in electronegativity great enough to be a polar bond, it does not necessarily mean the overall molecule is polar, because the spatial arrangement of the atoms might dictate whether or not all the positive charges are on the outside, and it would mean it's non-polar. Okay, so I'll give you an example of this. Okay. So one of the best examples of this, if we take methanol Okay, so methanol and aldehyde with the carbonyl group. Now oxygen has a great enough electronegativity to make this a polar bond. Don't be put off by the double bond, it'll make a difference. Delta negative, delta positive. Now the spatial arrangement of atoms here means that this molecule has a dipole. Okay? It's often denoted like that, which means that it has a negative top and a positive bottom. So this molecule is polar. Alright? And the classic example of one that isn't polar carbon dioxide Now, carbon dioxide does not have a dipole moment because electrons have been drawn away from both sides, which means it doesn't have a negative left and a positive right, negative top, positive bottom. So the spatial arrangement of atoms in this does not allow it to be a polar molecule. So this is non-polar. Okay. One other common example of polar molecules. This one's used quite a lot, which is trichloromethane. Now, this is not a polar bond, so we can ignore it. That's delta positive because each of these are delta negative. So this has a dipole moment, like that, so hence it's a polar molecule. Okay? But what they often like to do is you can play around with this molecule, because if we were to substitute this hydrogen for another chlorine, then there would be delta negatives all the way around the molecule, and hence it would then become non-polar. Right? So they're probably the most common examples that you'll find.